In the last video, we introduced the concept of anti-differentiation, the process used to find an antiderivative. So in general, the idea with anti-differentiation is we are reversing the process of differentiation. In other words, we're assuming that a function that we're given is a derivative. It's the derivative of some original function. When we find its antiderivative, we're reversing the process that was used to differentiate. We're asking the question, what function did we have to start with in order to get this particular derivative? The function we find that answers that question is called the antiderivative, or the indefinite integral of the function that we're given. So we also talked about some general rules we can use to find fairly simple antiderivatives. Now in this video, we're going to talk a little bit more about what the antiderivative actually means and how it can be used in application. So we're going to compare the derivative versus the antiderivative. Each of them means something very specific and is used a very specific way in applications. So in general, derivatives represent instantaneous change. So in other words, when we look at a function and take its derivative, essentially the derivative is allowing us to answer the question, how are our outputs changing at a single value of the input? Now antiderivatives, on the other hand, represent accumulation. So when we evaluate the antiderivative for a function and look at the values of the antiderivative, we're asking the question not how our outputs are changing, but how are our outputs accumulating as we transition from one particular input value to another particular input value. So you can kind of think of the derivative functioning like a microscope. The derivative takes a function and it zooms in to look at one particular location on the function's graph or one particular value of our input. An antiderivative is more like a telescope. It allows us to zoom out and get the big picture a little bit more for our function. And so we're looking at how our outputs are accumulating, how they're accruing as we transition across the function. So let's look at an actual application in relation to one that we looked at with respect to derivatives. So for example, if we have a marginal function, we discussed marginals when we talked about applications of the derivative. So a marginal function represents the change in output as our input increases by 1. So if we start with a particular input value of x and transition to x plus 1, a marginal function defined by the derivative tells us how the outputs change in relation to this change in input. Well, if you imagine taking the antiderivative of a marginal function, the marginal function resulted from differentiation. If you take the antiderivative and reverse that process, then the antiderivative of the marginal function represents a total amount. It tells us what the total value of the output is as we transition from where our function started to where our function currently exists, to the particular output or input value we're interested in. So we differentiate to get a marginal function. We can integrate or take the antiderivative of a marginal function to find a total function. In other words, to reverse that process of differentiation. So let's look at a couple of examples using this idea of how the marginal and how the total functions are related to one another. So a food purveyor has found that its marginal cost in dollars per kilogram of product is given by the following function. C prime of x is equal to negative 0.003x plus 4.25 for values of the input less than or equal to 500. And x is going to be given in the number of kilograms of product produced. So based on this, we want to find the total cost of producing 400 kilograms. So the function we're given tells us how the costs are changing to increase production by 1 unit. So for instance, if we were to plug in 400 to our marginal function, we're answering the question, how much additional cost would we incur to go from producing 400 kilograms to producing 401 kilograms? What would be the additional cost associated with that change? We want the total cost. So in other words, we want to know how much does the first unit cost, how much does the second unit cost, all the way up to the 400th unit, adding all of those costs together, representing the accumulation of cost. So I'm going to take the antiderivative of this marginal function, in order to yield our total cost function. So the total cost function is going to be defined as the integral, the antiderivative of our marginal function. And we're differentiating with respect to our input variable x. So I'm going to look one term at a time. I know in each of these cases I have a power rule, and then I have a rule that allows us to integrate just a constant by itself. So for the first term, I'm going to increase my exponent by 1, and then I'm going to divide by that new exponent. So my current coefficient divided by my new exponent, which will go from 1 to 2. And then for my second term, 4.25, it's just a constant, so when we integrate it, we reintroduce the variable x. And we know when we take a general antiderivative without extra information, we have our constant of integration c. Now for our purposes, we're going to let c equal 0. Now why is this? So the function we just found represents total cost. Okay, so when we look at a cost function, in general, a constant added on represents some element of fixed cost. In other words, if x were 0, in other words, we produced nothing at all, these two terms would go to 0, but we would still have some non-zero element of cost that represents a fixed cost. Well, we don't actually have any information in this problem about what our fixed costs might be. All we're interested in at the moment is how our costs accumulated in relation to things that are variable, namely how much we produce. So because we don't know anything about a potential value for C, a potential fixed cost, we're just going to assume that C is 0, and we're just going to focus on the terms that are impacted by our value for X. So we want to know what is the total cost for producing 400 kilograms of our product. In other words, we want to evaluate C of 400. So that's going to be negative 0.003 divided by 2 times 400 squared plus 4.25 times 400. And again, we allowed C to be 0, so that's going to be it. Now I'm going to plug that into the calculator, let it do the heavy lifting for you. So we have a coefficient of negative 0.003 divided by 2, and that's multiplied by our input squared plus 4.25 times our input. And that's going to give me 1,460. Well, 1,460 what? Our input is the number of units, the number of kilograms produced, and the function we were looking at was a marginal cost function and now a total cost function. So cost, of course, is given in currency. So that's going to be $1,460. So to produce from 0 to 400 kilograms, it costs us a total amount of $1,460. Okay, let's look at another example. So a bakery has found that its marginal profit in dollars per wedding cake produced and sold is P prime of X is equal to negative 0.12X plus 40, where X is the number of wedding cakes produced and sold. So we're going to assume that they make to order, everything they produce they immediately sell, there's not going to be a surplus. So we want to find the total profit from producing and selling 50 wedding cakes. So how much does the first one cost, plus the cost of the second, or rather the profit from the first, the second, all the way up to the 50th. What is that accumulated total profit? Well, we know how profit is changing to go from one production level to the next highest production level, to increase production by 1 unit. So if we integrate our marginal profit function, we reverse the process used to find the derivative, then we go from a marginal function to a total function. So our profit function is going to be defined as the antiderivative, the indefinite integral of our marginal function with respect to our input variable x. And essentially we do the same thing as we just did. So term by term, for our first term we're going to increase the exponent, so that'll become an x squared, and then we're going to divide by that new exponent. And then for our second term, 40, we integrate and that becomes 40 times x. And just for the sake of consistency, we need our constant of integration, but again we're going to let c be 0 in this case, since we don't know anything about any fixed values related to this function. Now I can reduce this if I want, or the whole goal is just to find an actual value. So we don't have to reduce our coefficient in order to plug values in and find the value we're interested in. So we want to know what's the total profit for selling 50 cakes. The profit for the first, the profit for the second, all the way up for the profit of the 50th, the total profit. So P of 50, I'm going to sub in 50 to my function, and again C is not there, it went to 0. So 0.12 divided by 2 times 50 squared plus 40 times 50. And so let's sub that in, let's evaluate that. So negative 0.12 divided by 2, there's our coefficient, times, you know what, let me put parentheses around the coefficient just to be safe. So negative 0.12 divided by 2, there we go, times 50 squared plus 40 times 50. And that's going to give us 1,850. And again, what is the unit here? Well, we're talking about profit, which is going to be in terms of currency. So that's going to be $1,850. So this idea of going from a marginal function to a total function, reversing the process that was used to differentiate and find a marginal function, is just one application of the antiderivative. So let's talk a little bit more about antiderivatives in general versus derivatives in general, specifically from a geometric standpoint. What does the antiderivative mean from a geometric standpoint? Well, we've discussed at length what a derivative means in terms of geometry, in terms of the graph of a function. So a derivative answers the question, how are our outputs changing at a single value of the input variable? So instantaneous change at a single value of our input variable. Now, graphically speaking, this is represented as the slope of the tangent line that would be drawn tangent to our function's graph at a single point on that graph. So if we draw a line that's tangent to our function's graph, tangent at that single point, then the slope of that tangent line tells us how our outputs are changing at that single value of the input. If we were to zoom way in using a microscope and look at that one point on the graph, it's the change in our outputs related to that particular input. Now again, an antiderivative represents accumulation. So what does that mean from a geometric, a graphical standpoint? An antiderivative answers the question, how are our outputs accruing? How are they accumulating as the input variable increases? So not focusing on what happens at a single value of our variable, but as we transition from one input value to another, how are the associated outputs accruing across that transition? So graphically speaking, this can be represented as the area under the function's graph between the two input values in question as we transition from one to another. So it all comes down to area, which is a very common geometric concept. So the goal in finding an antiderivative is, among other things, the goal of finding the area under the graph of a function, specifically between that function's graph and the x-axis, if we were to graph that function. So the approach we can take to finding this area, this concept behind the antiderivative, varies depending on the type of function we're looking at. So for really simple functions, specifically linear functions or constant functions, we can actually just use what we know about geometry, geometric formulas, to find the area under the graph. So in some cases, when we graph a function and we look at that function's graph over a range of input values, over an interval, what we essentially generate is a rectangle. So if we want to know what the area is under that graph, based on the fact that we've drawn a rectangular area, we just use the formula for the area of a rectangle. So the area of a rectangle is defined as the length of the rectangle's base times the length of that rectangle's height. So base times height, or length times width. The variables don't really matter, it's just the concept. So one dimension multiplied by the perpendicular dimension. Now in some situations when we graph our function and we look at that function's graph over a particular interval, we generate a triangular area. And so the area of a triangular region is defined as 1/2 times the base times the height. So if we look at the length of the base, if we look at the height of the triangle, multiply those two values and then divide by 2 or multiply by 1/2 equivalently, then we get the area contained in that particular region. So how do we indicate that we're looking for an area, that that's the goal? Well, of course, we could literally be told we're finding an area, but there's also a way of representing this concept of area using what we now know about antiderivatives and the notation we use for antiderivatives. So one notation we use to indicate that we're looking for a particular geometric area based on a particular function is what we call a definite integral. So when we were just defining the antiderivative, another name for the antiderivative was an indefinite integral. A definite integral is going to build on that. So we have our integral symbol, we have our function and our differential, but in addition to the integral symbol, we have two values, a and b. These are what we refer to as the limits of integration. So think of these as x values. A is an x value and b is an x value with a less than b. So essentially this definite integral is saying take the integral for our function f of x, find its antiderivative, and evaluate from x equals a to x equals b. So from a geometric standpoint, this expression, this definite integral, represents the area under the graph of our function, the accumulation of the outputs between the inputs x equals a and x equals b. And again, when we have a really simple, a really basic kind of function, in a lot of cases we can draw what this area looks like, and we can also evaluate that area, find what the actual area is, just using what we know about geometry and the two formulas that we've written down above. So let's try a couple of examples where we can use this idea of geometric formulas, how they relate to this integral. So we want to graph the region described by this particular function, the definite integral from 0 to 6 of the function 10 integrated with respect to x. And then we want to use our geometric formulas to evaluate that definite integral. In other words, find the area that this expression represents. Well, in this case, our function in question is the function 10. There's no x, it's just a constant function. Now, in order to better understand what this would look like if we were to graph it, remember f of x and y are interchangeable. F of x represents the output based on an input of x, but we could also write that as y equals 10. This is the equation of a horizontal line. So this would be the horizontal line that passes through the y-axis at y equals 10. So if we were to draw a horizontal line that passes through at y equals 10, then we have the graph of this particular function. You don't absolutely need a ruler, but for the sake of being neat, I'm going to use a ruler. So this is the graph of our function. So in evaluating the definite integral from 0 to 6 for this function, which we just graphed, we're asking the question, what if we just looked at that graph from x equals 0 to x equals 6? In other words, starting right here on the graph and transitioning to where x equals 6. That represents a particular area with a particular shape. So imagine drawing a line up to our graph, starting from x equals 0, and then ending at x equals 6. And then we're looking for the area contained within that region between the graph of our function and the x-axis. So that is the area in question. Notice in this case the area is rectangular. Because our function was linear, it was just a horizontal line. When we look at the bounds, that interval we've drawn from 0 to 6, it just ends up drawing a rectangle. So if we want to evaluate this definite integral, we can use the fact that the area that it represents is really just a rectangle. Well, what are the dimensions of the rectangle? Well, the base of the rectangle is determined by those values 0 and 6. So to transition from 0 to 6, we travel a total of 6 units. So the base of the rectangle has a length of 6. What about the height? Well, the height is what it takes to go from the x-axis up to the actual graph. And it's going to be 10 units at the beginning, 10 units at the end, a constant 10 units across. So that's going to be a height of 10. So we have a rectangle with dimensions 6 by 10. So if we want to evaluate the definite integral from 0 to 6 of the function 10 integrated with respect to x, we know this represents this area as drawn. And so we can find that area just using what we know about the area of a rectangle. So the area of a rectangle is defined as the base dimension times the height dimension. So in this case, that's just going to be 6 times 10. And if we multiply those together, we're going to get 60. 60 what, though? When we talk about area, area has a particular unit. Now, we don't know anything about inches, feet, anything like that. We just write in terms of units, but area is in terms of square units. So this would be 60 units squared. That would be our area. More generally, though, the value of this definite integral is the value 60. That definite integral evaluates to 60. So let's look at a slightly more complicated example, but one where we can still use this concept of the geometric formulas and how they relate to the definite integral. So we want to graph the region described by the definite integral from 0 to 5 of the function 2x integrated with respect to x. And then again, we want to use geometry to evaluate this integral. So what does this look like if we graph it and look at it from a geometric standpoint? Well, here our function is going to be 2x. So f of x is equal to 2x, or equivalently, y is equal to 2x. So this is also linear. It graphs as a line, but it's not the same kind of line. In this case, it's going to be a diagonal line. This is an equation that's now written in slope-intercept form for a line, which means our slope, the coefficient on x, is going to be 2. And then our y-intercept, which is normally a constant added on at the end, is going to be 0. So this is the line that passes through y equals 0, in other words, the origin, and has a slope of 2. We can think of that as 2 over 1, if that helps. So the rise is 2 and the run is 1. So I want to graph that line. So we're starting at 0, 0. So we're crossing the y-axis at a value of 0. And then to get to additional points on the graph, we use our slope. So we rise 2, and then for every 2 units we rise, we run 1. So rise 2, run 1. Rise 2, run 1. Rise, run, rise, run, rise, run, and then we fall off the graph. But that's certainly enough points to graph our line. So keep in mind, the line does continue in both directions indefinitely. So determining what portion of the line we want is going to be based on our values 0 to 5. So just like with the previous example, that means we're looking at just the portion of the graph that spans from x equals 0, which is right here, to x equals 5, which is right here. Well, at x equals 0, if we go to the actual graph, it's there on the x-axis. If we go to x equals 5, and then look at what it would take to go up to the graph to draw an area, then we end up having something that looks like that. And so if we look at the graph between the actual graph of the function and the x-axis, then we form a triangular region, a triangular area. So the area in question is going to be this particular area, a triangular area. It also just so happens that this is a right triangle. So we can find its base and we can find its height based on the intersection there at that right angle. So what's the length of the base? Well, we're going from x equals 0 to x equals 5, a total of 5 units. So the base has a length of 5. And then the height of the triangle takes us from the x-axis up to 10 for a total of 10 units. So our base has a length of 5, and then our height is 10. So if we want to evaluate our definite integral from 0 to 5 for the function 2x integrated with respect to x, this represents the area that we just drew. And we can calculate this area using our triangular area formula. So that says take the base, multiply it by the height, and then multiply that value by 1/2. So 1/2 times the length of our base, which is 5, times the height, which is 10. So simplifying that down, if you need the calculator, you can use it, but more than likely, you probably don't need it. So 5 times 10 is going to be 50. 50 times 1/2, cut 50 in 1/2, and you get 25. So 25 area, so square units. So that is going to be the area of that region, or more generally, if this is our definite integral, then it evaluates to 25. That is going to be the value of that definite integral. So with simpler situations where the function we're integrating, finding the antiderivative for, is simpler, something that can be graphed as a line specifically, we can use these geometric concepts in order to find the area of the graph, the area specifically between the graph of the function and the x-axis. But how do we find the area under a curve when the function is not linear? In other words, when there is no set geometric formula for finding area. Because most functions we graph are not going to graph as straight lines. As soon as we increase the exponent past 1, as soon as we use an exponent of 2 or an exponent of 3, those functions do not graph as straight lines, which means when you draw the area represented by that particular graph, which you still can do, there is no set formula to determine what the area between that graph and the x-axis would be. So we use a process called Riemann summation in order to approximate, not find the exact value for, but approximate the area under the graph over the interval in question from x equals a to x equals b. So we're not going to get an exact value for the area like we have for this triangle or the rectangle on the previous page, but we're going to get a very good approximation, and we have control over how good the approximation is. So we can have a very rough approximation, or we can take it a step further and we can make the approximation more exact. But again, keep in mind this is an estimate. It's not going to give us the exact value, it's just going to give us a good estimate. So here's what we're going to do. We're going to divide the interval, a to b, into subintervals of the same width. So divide it into parts. Divide a to b into parts. Then we're going to draw a rectangle associated with each of those subintervals. So each one is going to have the same width because each subinterval has the same width. And then in order to draw a rectangle, we need both a width, which is going to be the length of the base, and a height. The height for each rectangle is going to be f of x for whatever x value we've reached. In other words, the distance it would take to go from the x-axis up to the actual graph of the function. So we're going to draw rectangles that essentially span the interval from a to b, where the height of each rectangle is going to be the height that takes us up to the actual graph. And then we're going to find the area of each of these shapes. And at this point, it's just a bunch of rectangles. So we're just finding the area of a bunch of individual rectangles. And then we're going to take the sum of these areas. Add them all up. We have a bunch of different rectangles. Find the dimensions for each of them, take the area of each of them, and then add them up. And so once we add them up and get an approximation for that area, the area under the curve, what we actually want to approximate, is going to be roughly the same. How do we control how accurate the approximation is? That's going to be based on how many subintervals we divide into. So the more subintervals we break our interval into, the closer we'll get to the actual area. If we don't use many subintervals, we're not using many rectangles, we get a very rough approximation. If we use more subintervals, we draw more rectangles, we get closer to the actual area under the graph. So let's look at sort of a visualization of what this means. So suppose this is the graph of our function. A goes from the value x1 over to this value at b. So we're approximating the area under the graph all the way from A, where we start, to B, where we finish. Well, suppose we wanted to divide this interval into 4 subintervals. So we're taking the distance between A and B, which would be B minus A, and then we're dividing it by 4. So we're breaking it into 1, 2, 3, 4 equal widths, 4 equal subintervals. This is what we refer to as the common width. That's going to be the width we break that whole interval down into. And we're going to label this as delta x, change in x, because it's going to tell us how much we change to go from one x value to the next. And that's going to be a constant value as we transition across the whole interval. So delta x is defined as b minus a, so in other words, the total width of the interval, divided into the number of subintervals we want. So in this case, we divided it into 4 subintervals, so we would divide it by 4. Now, if we were to use 5 subintervals, or 6, or 7, or 8, however many we want, that value is going to change. So this is just going to be the number of subintervals. The number of subintervals. Okay, so essentially that is going to be the length of the base for each of the rectangles we're going to draw. So how do we draw the rectangles? Well, we're going to start at A, and then imagine just drawing a line to take you from the x-axis up to the graph starting at A. Well, that's going to be the height of your rectangle. So you have the base, you have the height, you can calculate the area of that rectangle. And notice what the height is actually going to be. Since we go from the x-axis up to the actual graph, what we end up with is the actual y value associated with that particular x value. Another name for that is f of that particular x value. So the heights for each of these rectangles that we're going to draw are going to be the y values, the function values, associated with the particular x value where we land as we transition across the interval. So in this case, we have 4 rectangles, which means we have 4 y values. We have 4 different heights. And again, each of these heights is going to be the function value associated with the particular x value where we land as we transition across the interval. So our heights are going to be f of x1, f of our first x value, f of x2 as we transition across a subinterval, f of x3 as we transition again, and then finally f of x4. Now, just as the number of subintervals can change, notice we have 4 y values here, 4 output values. That's because we have 4 subintervals. Say we wanted 6 subintervals. Well, we'd have 6 f values, 6 function values, and 6 heights, and 6 areas. So the total approximate area is going to take the area of each of these rectangles, rectangle 1, rectangle 2, rectangle 3, and rectangle 4. It's going to take each of them individually and it's going to add them up. So how would we evaluate the area for rectangle 1? Well, we're going to take the width of the rectangle, that base, which takes us from x1 to x2. That is going to be the common width. So every single one of these rectangles has a width of delta x because we took the whole interval and divided it into 4 parts, 4 equal parts. So the width is going to be the same for every rectangle. That's what we're calling delta x. So this is delta x. This is delta x as already labeled. This is delta x. And this is delta x as well. So what about our first rectangle? Well, its width is delta x and its height is going to be f of x1. It's going to be the y value associated with our first x value. So it's going to be delta x times f of x1. So that's going to be the area of our first rectangle. Rectangle 2. Okay, so our width, again, is still delta x. Now our height, to take us to this next point on the curve, is going to be f of x2. So plus the area of the next rectangle, so delta x times f of x2. Third rectangle, so delta x times the height of this rectangle. Notice it's the height on the left-hand side of the rectangle, so we're going up to the curve on the left-hand side of the rectangle, so f of x3. So plus delta x times f of x3. And then our last rectangle, delta x is our width, and we go up to the height at the left-hand endpoint of that interval, f of x4. So plus delta x times f of x4. So this is our rectangle 1, this is the area for rectangle 2, this is rectangle 3, and this is rectangle 4. Well, you may be thinking, how is this an approximation? Look at the rectangles. Rectangle 1 is too small, we've got this big gap. Rectangles 2 and 3 are too big, we have extra, and then rectangle 4 is also too small. Well, if you look at the area that you're missing in these 2 locations and the area that's in excess for those 2 rectangles, essentially the deficiency and the excess are going to balance one another out. So if you calculate how much you're missing in these 2 spaces and calculate how much extra you have in these 2, essentially they cancel one another out, which is why we end up with a good approximation. But the more rectangles we divide into, the less deficiency and excess we have, the closer we come to the actual value of our area. So there's no way to get the exact value using this approach. But again, the more intervals we have, the closer we get. So we can get essentially as close as we want. We can get close enough where the discrepancy is not really going to matter. So this is going to be our approximate area, but as you can see, writing something like that is pretty tedious. And particularly if you were to go to more subintervals. Here we only have 4, so we only have 4 terms, but imagine you were doing 20 rectangles, for instance. You'd have to write out 20 terms, which is very inconvenient. So fortunately, we have a sort of better notation for writing this that simplifies things down a bit. So we're going to use what we call sigma notation or summation notation, which uses the capital Greek letter sigma. So it looks kind of like an E. This is really a Greek S, though, S for summation. So that is going to be the symbol we use to represent that sum just in a more compact way. So what we wrote previously, we're going to write using this notation, this new notation. So there's my sigma. I'm going to write upper and lower values below and on top of the sigma. So those values are going to tell us how we transition from one x value to another. So notice the subscripts. We go 1, 2, 3, 4. We start at 1 and we transition to 4. So those are going to be indicated, how we transition, that's going to be indicated below and above our sigma. So we're going to introduce what we call the index of summation. I'm just going to use I. I is pretty common. We can use pretty much anything we want. And I is going to be equal to 1 to start. So this is the value where we start. And we notice the last value we had for our subscript was 4. So the upper value I'm going to put on top, that's going to be 4. And then next to my sigma, essentially I'm just going to write out a formula for what each of these terms looks like. Because notice the terms are structured very similarly. Delta x is the same for all of them, and notice the only thing that's changing is the subscript on our actual x value, so x1, x2, x3, x4. So if we think of this subscript as being the value that's changing based on that I, based on the index of summation, then we can write a formula for what each of these 4 terms looks like. So each term is going to be structured as delta x times f of x with a subscript of I. So what this notation is telling me is use this formula, this is how my terms are going to be structured, and write each term going from I equals 1 to I equals 4, and then the sigma says take all of those and add them all up. So all of the terms that look like this, starting at I equals 1, going from 2 to 3 up to 4, write all 4 of the terms based on those values of I, and then sum them, sigma sum them. So this notation is probably new to a lot of you. So let's do a little bit of practice interpreting what this means before we actually use the notation any further. So we want to express each of the following without summation notation. In other words, interpret what this symbol is really telling us to do. So suppose this is what we see. So in other words, we are summing using the index I, transitioning from I equals 1 to I equals 4. In other words, 1, 2, 3, 4. Those are going to be the values for I. And this is the formula for how we generate the terms. So each term is going to be of the form 3 to the power of I. And so we're just going to apply the values for I starting from 1 and going to 4. So this is the same thing as our formula applied with a value of 1, so 3 to the first power. Add on each subsequent term with that formula applied to the next value of I. So 3 squared plus 3 cubed plus 3 to the 4th power. That is what this notation really means. This is the expression, the expanded form that expresses what this notation is actually telling us to do. And of course we can simplify that because we have a calculator. So 3 to the first power is just 3 plus 3 squared plus 3 cubed plus 3 to the 4th power. And we simplify that, and that gives us a value of 120. So this expression really just simplifies to a value of 120. Now what about the next one? Okay, so similar idea, our index is I, and we're transitioning from 1 to 6, and this formula is telling us how we generate the terms in that, what we call a series. So we start from I equals 1, plug 1 into the formula, then we go to 2, plug 2 in, all the way up to 6. So this is saying, and I'm going to put parentheses because notice we have more than one term within each thing we write based on our different values of I. So we have 1 squared plus 1 plus 2 squared plus 2 plus 3 squared plus 3 plus 4 squared plus 4 plus 5 squared plus 5 plus 6 squared plus 6. And so ideally, it's not a good idea to plug this all into your calculator at one time, but maybe just simplify each of these terms individually. So 1 squared plus 1. Well, 1 squared is 1. 1 plus 1 is 2. Okay, 2 squared is going to be 4. 4 plus 2 is going to be 6. 3 squared is going to be 9. 9 plus 3 is going to be 12. 4 squared is 16. 16 plus 4 is 20. 5 squared is 25. 25 plus 5 is 30. And then 6 squared is 36. 36 plus 6 is going to be 42. And so now I can just plug all of that in and simplify that. So 2 plus 6 plus 12 plus 20 plus 30 plus 42. And we get a value of 112. So this particular sum evaluates to a value of 112. Okay, so let's go back to the actual application. We're looking at this idea of the area under a curve. And so again, we determined that we get a decent approximation of area. Where we're missing some area, it's complemented by extra area above in different regions. And so overall, everything kind of balances out. But again, as we increase the number of subintervals, which also has the effect that we decrease the width of each rectangle. We're looking at the same interval either way, but if we increase the number of subintervals, then each individual rectangle is then going to be smaller. We find a better and better approximation of the area under the curve. So suppose we were to divide into 8 subintervals. Well, we calculate the area of each of these, combine them together, and we get a better approximation than we did before. So again, we have some spots where we're missing area, and we also have some spots where we have too much area, but essentially they balance each other out. Think about taking the excess and filling in the spots where we're missing some. So for instance, this region right here almost fits into this gap right here. This particular region would almost fit into this gap, and then so on and so forth for the other two. Now, if we were to increase to 24 subintervals, notice how much closer we get to the actual area. And you can see the discrepancies are smaller and the excess is also smaller. So if we were to take the area based on 24 rectangles, we get even closer than we were before. So conceptually speaking, we can't actually do this, but conceptually speaking, if we were to allow the number of subintervals to go infinite, well, we can take a limit here if we allow them to approach infinity. We've looked at that kind of thing before. We can't literally draw infinitely many rectangles, but we could draw 100 or 1,000 or 1,000,000. We can take a limit of the number of subintervals, that would give us, conceptually speaking, the exact value of the area under the curve. Do we actually have to do that? Well, it really just depends on the situation we're in. So ideally we want the exact area, but it's really a question of how accurate do we really need it to be? How close is good enough? And the answer to that question just varies based on the situation that we're looking at. So that's the idea behind it. Let's actually practice finding some of these areas based on the graphs we have. Just getting this area based on this idea of rectangles, drawing rectangles, and calculating the area of those rectangles. Okay, so we want to use 5 subintervals to approximate the area under the graph of this function. Definitely not a linear function, which means there's no standard geometry formula that will allow us to calculate the area under this graph. And we want to look specifically over the interval from 1 to 16. In other words, from x equals 1 to x equals 16. Well, let's graph what this function looks like for more reasons than one, and we'll see why in just a minute. So I'm going to graph my function. So 0.1 x cubed minus 2.3 x squared plus 12x plus 25. And I'm going to graph that. Okay, so it looks like maybe we can only see one portion of the graph, so I'm going to zoom out a little bit. Let's see if we can see more. Okay, now we get a better picture. So imagine evaluating the area under this graph as we go from x equals 1, which would be roughly there. You can see I took the arrow, tabbed over, and now we're close to x equals 1, all the way up to x equals 16. I went too far. Let me go back a little bit. I'll get there eventually. There we go, roughly there. So imagine taking that particular region between those two x values, and we want to get the area under the curve between those two x values. Okay, so visually speaking, that's what we're looking at. So if I were to just sketch roughly what we're looking at, here we go. We're essentially looking at something like, looks like maybe something about like that, going from x equals 1 to x equals 16, which is somewhere over there. And so the question is, what is the area under the graph between x equals 1 and x equals 16? So in order to approximate this area, we've been told we want to use 5 subintervals. In other words, we're going to take this whole span from x equals 1 to x equals 16. Notice they are 15 units apart. And we want to break that down into 5 subintervals, hence 5 rectangles. So first thing we need is our common width. How wide is each of those rectangles going to be? Well, we're going to do our delta x, so change in x. Change in x is equal to the difference between our upper x value and our lower x value. And then we're going to divide that into those 5 subintervals. And so our numerator goes to 15. Our denominator is still 5. So that means the width of each rectangle is going to be 3 units. So from a practical standpoint, that means we're starting at x equals 1. The next x value we transition to is 3 units above that. So it would be at 4. And then 3 units above that, which would be at 7. And then so on and so forth until we've drawn 5 rectangles. Okay, so let's write the expression for the sum for this area. So what is each of the individual rectangles going to look like? So we can't really draw them here, but you get the idea. Here would be the first rectangle, something like that. Then we'd have another rectangle that looks like that, and then so on and so forth. Each one has a width of 3 units, and then we go up to the height. We go up to f of that particular x value. Okay, so our first rectangle is going to start at x equals 1, and so our width will be 3, our height will be f of 1. The next one is going to be at x equals 4, so 3 units away, and then a height of f of 4. So let's write the summation notation for what we're going to evaluate. So we're using 5 subintervals. In other words, our index is going from 1 to 5. And then the actual area is going to be our delta x, the width, times the height, which will be f of the particular x value we get to, which is the first x value and then the second all the way up to the 5th x value. So we write that as x sub I. Okay, so now we need to apply what this is telling us to do. So start with 1. Okay, starting with our first rectangle. We're starting at x equals 1. Okay, so for our first rectangle, delta x, that's going to be constant. It's always 3, so the width of that rectangle is 3, times the height of that rectangle, which will be f of our first x value, f of 1. Okay, now we move 3 units over. So plus the area for our next rectangle, it has a width of 3, times the new y value at that new x value. Well, we started at x equals 1, so we transition 3 units over. So we go from 1 to 4. So this is going to be the first rectangle. I'm going to label these. So this is rectangle 1. This is rectangle 2. Okay, keep going. So our next width, also 3. And then the height is going to take us up to the next x value, f of the next x value. So 1 to 4, 3 units apart. Add another 3 units, and that'll take us to 7. So f of 7. Okay, so that's going to be rectangle 3 plus the area of the next rectangle. So our width is 3 times the height. Well, we're at x equals 7. 3 units away takes us to f of 10. So that's rectangle 4. And then rectangle 5, again a width of 3. And then our height, starting at 10, we go to 3 units above that, which is 13. So f of 13. And that's going to be rectangle 5. Now you may be looking at this and thinking, well, we didn't cover the whole distance. We didn't get to 16. But technically we did. So think of it as we're starting at 1 and then we're distributing the width to take us to 4. And then we're starting at 4, distributing that width to take us to 7. And then 7 plus 3 takes us to 10. 10 plus 3 takes us to 13. And then 13 plus 3 takes us to 16. So even though we don't have f of 16 here, we make it all the way from 1 to 16 based on the fact that we're transitioning 3 units across to go from one x value to the next. So now it's just a matter of actually simplifying all of this. And this is another great place where your calculator is going to be very helpful. Now, one thing I want you to notice first off, we have 1, 2, 3, 4, 5 terms. And notice that common width is there within each term. So we can think of it as a greatest common factor. We can actually factor it out so that we only have to multiply by 3 the one time. And so we're multiplying 3 by the sum of each of those values for f of x. So f of 1 plus f of 4 plus f of 7 plus f of 10 plus f of 13. So then the question is, what are these values? Well, literally, they're the values we get when we evaluate this function at 1, 4, 7, 10, and 13. So we can manually do that, or we can see if the calculator can help us do that. And that's where the table function on the graphing utility is going to be helpful. So I'm going to go into the table, and I have a little bit of stuff left over. I'm going to go back and change my table settings. I have them set on ask for the independent variable so that I can type in values. I'm going to change it to auto because notice the only values we want are going to be integer values anyway. So setting it to auto is going to take care of that. So we can just immediately pull off those function values based on what we see in the table. So when x is 1, the function value is going to be 34.8, so that's f of 1, plus f of 4, well, our function value there is 42.6, plus f of 7, we get 30.6, plus f of 10, which is 15, plus f of 13, which is 12. There we go. So it's our common width multiplied by each of those individual heights for our 5 rectangles. So now I just need to plug that in and evaluate that. So 3 times 34.8 plus 42.6 plus 30.6 plus 15 plus 12. And there we go. And so that simplifies down to 405. So this is going to be the approximation of the area under the graph of our function as we go from x equals 1 to x equals 16. So this is not the exact area, not by any means. If we were to use, for instance, 6 or 7 or 8 subintervals, we'll get a little bit closer. The area may increase, it may decrease, it's just going to depend, but this is a rough approximation of the area under the curve. Okay, let's try another example. So we have a new function, f of x is equal to 300x minus 1/2 x squared, and we're looking over the interval from 0 to 600. In other words, from x equals 0 to x equals 600. So a large span, a large interval, all the way from 0 to 600. And we want to use a Riemann sum to approximate the area under the graph, first off using 6 subintervals. So 6 subintervals dividing the region under the graph from 0 to 600 into 6 subintervals. So let's graph this function, see what this looks like. So 300x minus 1/2 times x squared. There we go. So we don't really have a great graph here. As soon as you see large values, you may not get the whole picture based on what you're looking for. So even if you continue to zoom out, you still may never get a really satisfying picture. Well, now we can see a little bit more of the graph. So what happens if I continue to zoom out? Well, I'm getting there. Notice there's 2 sides to it. Okay, and the further we go, I don't know that we're necessarily going to get a better picture. But based on what we know about functions in general, this is a quadratic function. It's shaped like a parabola, which means if we really were to look at the graph, based on what we're seeing now, it looks like we have something like that. We have a function that's shaped like that. So we want to know what's the area under the graph as we go from x equals 0 to x equals 600. And here we're approximating by dividing this interval into 6 subintervals. So first off, what's the width? How wide is each rectangle going to be? How far are we going to go to transition from one x value to the next? Well, our width, delta x, is going to be the difference between our endpoints, so 600 minus 0, divided into those 6 parts. So our numerator is going to be 600. 600 divided by 6 is going to be 100. So each rectangle is going to be 100 units wide. To go from one x value to the next, we transition by 100 units. Okay, so let's write our expression based on that. So we're taking the sum over 6 intervals. So from I equals 1 to 6. So we're summing up the area for each of these 6 rectangles, and the area is defined as our common width multiplied by our function value at each associated x value as x goes from, that should be an I, as x goes from I equals 1 to I equals 6. Okay, so let's put that in context. What does that mean here? What is I going to be in each of these cases? Well, I is going to be 1 to 6, but what are the actual x values? Okay, well, delta x, we know that's constant, so we're starting with our first rectangle. It has a width of 100 units times the function value associated with the first x value. Well, our first x value is 0. Okay, so our first f value is going to be f of 0. So this is the area of rectangle 1. Now, as we go to rectangle 2, how do we get there? Well, we're starting at x equals 0, and then the width of each rectangle is 100 units. So we go from 0, 100 units across, which would take us to the next value of 100. So the width of the rectangle times the output at the next x value, so f of 100. So that's going to be rectangle 2 plus next rectangle, so the width is 100. Where's the new x value? Well, we're now at x equals 100. We transition 100 units across, which takes us to 200. So f of 200, this is going to be rectangle 3 plus next rectangle, 100 units across, times the height. Well, we're at 200. We transition 100 units across, so we get to 300. So f of 300, that's going to be rectangle 4. And then you get the pattern. You can probably see where this is going. So our next x value is going to take us to 400. And we wanted 6 rectangles in total, so one more rectangle. The last rectangle is 100 units across, and its height is f of 500. And again, notice we don't get all the way to 600, but we're starting at x equals 500, going 100 units across, which would take us to 600. So we do cover the whole span from 0 to 600. Now, just like before, structurally, the same thing's going on. Notice we have that common width. That's a factor in each term, so I can factor that out. And then I'm just looking at my function values. So f of 0 plus f of 100 plus f of 200 plus f of 300 plus f of 400 plus f of 500. And as before, let's let the calculator do the hard part. Now, if I just go into the table now to get those function values, I'm going to have to scan for a long time to get 100, 200, 300, so on and so forth. So this might be a good time to change back to ask for the independent variable. That way we can just type in the x values that we want. So once that's set, I'm going to go back into my table. So the first value I want is f of 0. Well, f of 0 is 0. Why is that? Well, think about plugging it in here to the actual function. You plug in 0, you plug in 0. 0 minus 0 is 0. So our first function value is just 0. Now what about f of 100? Plug that in. We get 25,000. So we're getting big values, which is not necessarily surprising, just based on the kind of function we have and what we saw with the graph. Okay, f of 200. 40,000 plus f of 300, which is going to be 45,000, plus f of 400, which is going to be 40,000, so it looks like we're decreasing again, plus f of 500, which takes us back to 25,000. Okay, so now we just need to evaluate this. So 100 times my sum, 0 plus 25,000. Double check your zeros here. Make sure you don't add too many. Make sure you don't leave one off. Plus 40,000 plus 45,000 plus 40,000 plus 25,000. There we go. Big number. So double check again, how many zeros do we have? We have 5 zeros. So I'm going to go ahead and write it down and then we'll figure out what that is. So 175 and then 5 zeros. So we put the commas in, working our way from the lowest place to the highest. So 3 and then, oops, should go between the 7 and the 5. Apologies. So what is that? That's 17 million. Why did we get a number so big when the other number was so small? Well, it's the difference of function values. We're talking about a function where the outputs are much larger than the outputs were with the previous function. So it makes sense if we're accumulating all of those outputs that we end up with a big number. Okay, let's try one more example. I want to take the same function, but what happens if we divide our interval into more subintervals? So we just did 6 subintervals. What if we divide it into 12 subintervals? So we don't have to keep flipping back and forth, I'm going to go ahead and write down the function here up at the top. So our function was 300x minus 1/2 x squared. So 300x minus 1/2 x squared. And we're looking at the interval from 0 to 600. Now, as you can probably guess, if we're doing 12 subintervals, it's going to be 12 terms, which means it's going to be more writing. But it also means that we're going to get a better approximation of the area. So first off, what's the width going to be? Well, because we're increasing the number of subintervals, increasing the number of rectangles, but still distributing them over the same distance, each rectangle is going to be smaller, so each width is going to be smaller as well. So delta x in this case is going to be 600 minus 0 divided into 12 parts. So that's going to be 600 divided by 12. 600 divided by 12 is going to be 50. Well, that makes sense, right? Because if our original ones were 100 units across and there were 6 of them, then if we double the number, each one is going to be half the width that originally was. So each rectangle is going to have a width of 50 units. Okay, so let's set up our sum. So we're taking the sum from one rectangle up to 12 of delta x, the width for each rectangle, times the associated height, which is going to be the function value at each of those x values. Now I want you to notice something. Notice in this case, the index is only going to apply to f of x sub I. This delta x, we could really just go ahead and sub in a 50 right now. So let's do that. So that's going to be I is equal to 1 to 12. Delta x is the constant value 50. And then we're multiplying that by f of x I. Notice in the previous 2 examples we did, we ended up factoring out that common width because it was a common factor among all of the terms where we calculated the area. Because it's a constant, it's not going to change as we transition from I equals 1 to I equals 12. So we can actually factor it out of the sum, and we saw the result of that in the previous 2 examples. It doesn't affect how we transition across the sum. So we can actually just go ahead and factor it out, only apply it that one time at the very end, and save ourselves a little bit of writing. So the only thing that changes is anything where the index applies. So in this case, f of xi. So let's write out what the sum is going to be. And again, preface, it's going to take a little bit of writing. It is what it is, but we're going to get a better approximation of our area. So 50 times our sum. So our first x value for our first rectangle is going to be at 0. That's where we start. So f of 0. So this is rectangle 1. Now we're transitioning 50 units across this time. So we're starting at 0, transitioning 50 units across. So the next x value we end up at is going to be 50. So this is associated with rectangle 2. Now keep in mind, these are not the areas of the rectangle, but if you were to distribute that common width, we would have the area. So these are the outputs, the heights associated with each of these rectangles. Okay, 50 units more across, so we go to 100. And by now you can probably see the pattern, but it is worth making a note. Make sure you get all the way to 12 rectangles. So 50 units across, we transition to 150 with rectangle 4. 50 units across, we transition to 200 with rectangle 5. 50 units across, we transition to 250 with rectangle 6. 50 units across, we transition to 300 with rectangle 7. 50 units across, so 350 with rectangle 8. 50 units across, so 400 with rectangle 9. We've got 3 more. So then we go to 450 with rectangle 10, 500 with rectangle 11, and then 550 with rectangle 12. Now again, why did we not end at 600? Well, imagine distributing your 50, that's the width for each rectangle. When we distribute the 50 to our last term, that says starting at 550, we're transitioning the 50 units across. So from 550, 50 units across, takes us to 600. So we do enclose that entire area over that entire interval. So just like before, now we need to evaluate these particular function values. But we already have the 50 factored out, and so that saved a little bit of writing. Now some of these we already have. Keep in mind, this is the function we already graphed. So some of these values we already have. We'll just need to add on as we go. So starting at 0, we had f of 0 is 0. What about f of 50? So f of 50 is going to be 13,750. F of 100 we already have. That was 25,000. F of 150 is going to be 33,750. F of 200 we already have, that was 40,000. Notice our outputs are increasing. If you think about the shape of the graph, there's a reason for that. Okay, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so next 250, okay. So 43,750. Okay, so 250 to 300, which we already have, so that's going to be 45,000. Okay, 350, 43,750. Notice we get repeated outputs, so it looks like 45,000 is the area around which we peak. We could verify that with the derivative, right? We know how to do optimization, maximization problems. We could do that. Okay, so we went from, let's see, 45,000 was at 300, so 350 to 400, which would be 40,000. You can probably see how it's easy to lose track of the numbers. Okay, and then 450, which we need. So 33,750. 500 we have, that's 25,000. And then then 550, add on, that's going to give us 13,750. Now, to be sure, we had 12 rectangles, so we should have 12 terms. So double check by counting. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, notice how the values transition. We get to 45,000 and then we repeat our outputs as we continue on. So that's going to be our value. Now, in order to save us some time typing all of that in, and to keep us from potentially making mistakes, I want to simplify things a little bit here. Well, how do we simplify it without the calculator? Well, it may help to think about how many terms we have in common. So first off, the 0 we don't need. But notice we have repeated values, so we can indicate that. So 13,750, we see that 2 times. So there's 2 of those in our sum. So I'm going to write that as 2 times 13,750. So I only have to type in 13,750 one time. So I'll underline them as I go so we know which ones we've covered. So 25,000, there's 2 of those. So plus 2 times 25,000. So we've gotten those. Okay, 33,750, there's 2 of those. So plus 2 times 33,750. Okay, we've got 2 40,000s. So plus 2 times 40,000. We have 2 43,750s. So plus 2 times 43,750. And then notice we only see 45,000 the one time. So plus 45,000. Now this step is entirely optional. You can still type it in here and you'll get to the right answer. This is just one way to maybe clean it up a little bit so you don't have to do as much typing and you don't risk maybe leaving something off. Even just leaving a single 0 off or adding an extra will change your final answer. So optional, but potentially worth doing. We need to make sure we use parentheses though if we're going to take that strategy. So 50 times 2 times 13,750. Okay, so notice we have double parentheses now. We have parentheses nested inside of parentheses. Okay, plus 2 times 25,000 plus 2 times 33,750 plus 2 times 40,000 plus 2 times 43,750 plus a single 45,000. And then we close the parentheses. So I highly recommend with this one in particular, arrow back to the beginning and double check everything you typed. Make sure you have the right number of zeros. Make sure you've closed parentheses each time you open a set of parentheses. Those are going to be important things to double check before you hit enter and evaluate this, because those kind of mistakes can make a major difference. So once we're satisfied, there we go. So again, I'm going to write that down and then we'll determine where the commas go. So 1, 7, 8, 7, 5, and then 3 zeros. So to put in the commas, we go 3 zeros in and then 3 more places for 17,875,000. So how does that compare to the previous area we found for this particular function? Well, the previous area was about 17.5 million. This is a little bit bigger, so about 17.9 million. This would be a closer approximation of the area than the previous one because we have more rectangles. We divided our interval up into more parts. So because the rectangles are now smaller, the approximation is going to be closer to the actual area that we would shade underneath our curve. So this is just one application of the antiderivative of a definite integral, this idea of finding area under a curve. Now we're going to learn in the next video how we would get around this issue with approximation. So the idea of a Riemann sum in some ways is the fundamental version of finding an integral, finding a definite integral. There are other ways to find definite integrals too, but what we end up doing stems from this idea of the Riemann sum, this idea of approximating the area under the curve using these repeated rectangles. So we now have a sense of how we can use the antiderivative, what it means geometrically, and we'll build from there.